It's Cinta online. She had some problems to join. Oh, perfect. Cinta is joining. And we have John as well. So I think we're just missing Kees. He was sending a messages.
Have you put it, because it's still not joining, have you put it open for registrants, please? Because we said they could join 10 minutes before.
Yes,
it's working. Yeah,
it is. So Antonio, could you please stop sharing your screen? So we're just missing Kees.
And Sarah, when you share the screen, can we then use our mouse to point to something or not?
Oh, good question. I don't think so.
No, I don't think so.
No, I don't think so. And the other thing is that it's a bit, because you will see the screen, so you will not see me, and I will try and be strict with the time. So the only thing I can think of is that 1 minute before I will have to break in and say 1 minute. This is not very elegant, but that's the only solution I've found so far that we can do, because normally the moderator can wave a little piece of paper or something, and that's unfortunately not possible. So
I'm going to share to try. It is done, I think.
Oh, okay. We have Kees here as well. Very good. So
yeah, it's been
Kees,
a challenge.
You're on mute, Kees.
So welcome to the participants who are joining us. We will start at 10 o'clock, but at the moment we're just checking technical aspects.
Good morning.
Hello, good morning, Kees.
Good morning.
Sarah, just a question. Who's showing maybe
We can't hear you very well.
Who will show the slides? Will you do it from the central station, or I do it locally?
As you prefer, Kees. I can do it, or you can do it yourself. So
if you can do it, I would be happy.
Okay. So I will share the screen for Kees and for Erik. Is there someone else who wants me to share their presentation? No.
It's okay.
Okay, good. So and then the others, please, during the presentations, keep yourself muted so we don't have any interruptions. And I mentioned that I will be keeping the time, so please pay attention to keep your time, because I will have to break in and say 1 minute when there is 1 minute left, and that's unfortunately not very elegant, but normally you cannot see you will not see the chat or the other panelists, so I will have to do it like that.
Maybe just a comment which addresses both panelists and all registrants. If you have questions, please use today the chat function rather than the questions and answers, because the questions and answers, we don't seem to be able to record it and safeguard it and so retrieve it afterwards. Whereas we have a record of the chat, which means we can find the questions and make sure we don't miss any. So please use the chat function for any questions and comments. You can either send questions direct to the speakers or questions and comments to all registrants.
Okay.
So do you want to put the first slides up, Bengt? So we're ready to start at 10 o'clock, which it now is.
Okay, so it's 10 o'clock. So welcome everyone to day 2 and session 2 of our workshop on iron phosphate. We have had a very good interest in this workshop with over 500 people registered. In yesterday's session, we had almost 300 people joining us. So that was very positive. So yesterday, we were speaking about iron phosphate interactions in different systems. And today's session 2, is on iron phosphate usage in agriculture. So I welcome our first speaker, Bengt Hansen from Kemira. Please, Bengt. So yes, before we start, again, a reminder, we'll have time, I think, for 1 or 2 questions after each speaker. And please use the chat for communicating with each other. Normally you can send messages to each other as well as to all attendees and panelists. And the panelists are also welcome to engage in discussions there. Maybe we can respond to some questions already there. So yes, please go ahead, Bengt.
Hey, thank you. So I start this day, and I can't say anything about the nice conference dinner the evening before, because that we haven't had the opportunity to do this time. My name is Bengt Hansen, and I work as an application manager in Kemira with municipal water treatment and sludge, including phosphorus recovery. And I will talk about iron and the bioavailability, or some studies around that. First of all, I would like to repeat this, that iron and alumina salts are important to reach low levels of phosphorus in treated water, because that's the main aim with them. We have to remove the phosphorus in water, and the coagulants, iron and alumina salts, will be there in the future as well, if we want to reach these strict values. Otherwise, it will cost more in investments or in energy. Phosphorus bioavailability is a very heavily debated question, and I will show some cases where I see it from the positive side. And there has been a lot of studies over the years, and I think the design of the studies varies as much as the results. So I start already 1932, when I was Googling phosphorus availability on iron and aluminum. I found this publication from the University of Arizona, where McGeorge and Breezel concluded that phosphorus was available in ferric and aluminum salts. I highlighted the results and also the question mark here. So they said that in general, the opinion was that there was a poor availability of these media, but the experiments shows that it was an excellent assimilation of phosphorus from these 2 salts that were aluminum and iron salts. So that was one study that I found. And then we move forward to a second study. And here we again are doing tests with ferric phosphate. Maybe because McGeorge and Breezel weren't convincing enough, there has been a lot of other studies, and this is one then, where Richards and Johnston studied a lot of different recycled phosphorus sources. It was around the millennium. Amongst those, there was one recycled material that was ferric phosphate, and they studied it on 2 soils, amongst all the other sources they studied, and they used raygrass for the test. Totally, the harvest did 7 times, and the study was going on for 100 days. They used monocalcium phosphate as a reference, and you can also see a picture from another trial here with ferric phosphate compared with 2 phosphate and no phosphorus at all, just showing that there is growth in the ferric phosphate. So on this first graph, we can see that the yield, the plant yield, gram per pot, was the same monocalcium phosphate as ferric phosphate on both soils, maybe even surprisingly a little bit higher on ferric phosphate on soil 2, especially since the pH in that soil is higher than in the soil 1. They also showed the uptake of phosphorus in this study. And we can see here that they measure the uptake of phosphorus in the plants after each harvest. And in the beginning, the first couple of harvests, the monocalcium phosphate was more available than the ferric phosphate. But over time, the ferric phosphate catch up. And you can see that after 4 and 5 harvests, the uptake of phosphorus is as good with monocalcium phosphate as with ferric phosphate. So my conclusion from this study is that the phosphorus is available also in the ferric phosphate. However, it might be a little bit more slowly available. And of course, that depends on the soil chemistry as well as on the plants, the mycorrhiza, and a lot of other stuffs that I'm not for sure an expert in. Another study was done by Water Environmental Research Foundation in the US. Their study was basically to take a look at the runoff and erosion from agricultural land when using different kinds of organic fertilizers. And sludge was amongst those. And they also took the opportunity to measure the solubility in very many different ways, because that's one of the debates when we talk about ferric phosphate. Ferric phosphate is not available because it's not soluble. And you can look at the graph or the table afterwards, what kind of methods they used. What I would like to show here is that when plotting the yield for 2 years, the 2 years trials, versus the solubility of phosphorus depending on some of these different methods, I would say that the correlation is very, very poor. There is a weak correlation between water extractable phosphorus and the yield, but if you use oxalate or citrate, there is no correlation at all. Some other results from this study was that they saw that when the metal to phosphorus ratio on molar basis is higher than 2, the plant yield dropped a few percent compared when using NPK as a fertilizer. Another interesting finding, and of course that was the purpose with this trial, was to find out about the erosion. And when you had a high content of iron and aluminum in the sludge, that gave a significant reduction of erosion and of phosphorus from the soil during heavy rainfalls. The fourth and last example is a Swedish study, not far away from where I live in South Sweden. It's made by Hushållningssällskapet, a very long Swedish word, translated to Swedish Rural Economy and Agriculture Societies. This is a very long trial. It has been going on since 1981. And I present the results here from 2015. The results, the next report will be published this year. And for the first time, it will also be translated into English. And I think this is a very, very well reported and long-term study. And of course, it should be spread also internationally. I would say it's probably the best sludge trial ever done in the world. They use 9 different dosages, 4 replicates on each. You see on the upper right how they have placed the different dosages. They have with and without sludge. They spread the sludge every 4th year. And they also use with and without NPK. When they always try to compensate for the nitrogen if they use a sludge, so that will not be an issue, and the potassium. So that will not be the factor that change here. They also use 2 different farms, so 2 different soils and 2 different sludge types. Both are iron-based sludges, but one also has some aluminum in it. You can see the lower right is for the 34 years of field trial, that the PAL is increasing somehow. PAL is the standard use for phosphorus availability in Sweden when applying sludge. It's increasing some, whereas without sludge it is around 10 all the time. We can also see some other nice and interesting experience from these trials. If they used no fertilizer at all or used sludge, the increase was 16% in average over this time. When you combined fertilizer and sludge, you had an average a 7% yield increase compared with using fertilizer only. And for these farmers, that was an increase in value by 50 to 100 euros a hectare a year. You can see here the upper right that the dark green is the yield with a combination of fertilizer and sludge, and the other one is with fertilizer only. Remember that it's the same dosage of NPK here, so it's not an overdosage with the sludge.
1 minute, Bengt.
Yeah, okay, so we come on up here. I just want to say also that the uptake of cadmium and other metals was the same with when sludge was done or used, or when NPK was used. There were no issue there. The initial years, there was some increase of copper and mercury in the soil because the sludge had a very high content of copper and mercury at that time. Today, it's flattened out, so there is no difference over time on the heavy metal content. Last, just a conclusion. I would say that phosphorus precipitated by iron and is available for plants. It is used, when sludge is used as a fertilizer, the solubility test of phosphorus showed none or limited correlation to the plant yield. Only when the water soluble gave some correlation. Short-term trials give completely different results than long-term. Soil chemistry will balance up things. And 34 years of trials shows that it's possible to increase the yield by 7%, and the crops do not take up more heavy metals, even if the heavy metal content in some cases has increased slightly over the year. So I take it from there, and I'm open for questions. Thank you.
Thank you very much, Bengt. I do indeed think we have a couple of questions from the audience. Chris, do you want to pick up some questions?
Yes, I think that there are 2 initial questions. Firstly, how is the value of the phosphorus in sewage sludge affected by the levels of phosphorus already present in soil? Maybe that's the first question.
I must say I can't answer that question because I'm not sure I get it. So I mean, there of course are phosphorus in the soil from the beginning, but if you see an improvement in some cases, then of course it is a matter of how the baseline of phosphorus and what you add. So if you compare with the reference where you see that it's an improvement when you add also a ferric phosphate.
Another question, are these acidic soils? What is the soil pH?
I can't say directly. I have to look back into the reports on the soils in southern Sweden. It's quite much calcium, so I would say it's not an acidic soil.
Okay, and the sludge is from municipal wastewater treatment plants in each case?
Yes, they are both from municipal wastewater treatment plants, and both used iron salts to coagulate phosphorus, and one also used some aluminum salt.
Okay, and just a final clarification on the Sweden study. When sewage sludge was used, did that mean that the soil was receiving more nutrients than when only fertilizer was used?
No,
or
they adapted.
Comparison with. Okay.
They adapted the dosage.
Okay, right. So it was effectively the same amount of nutrients, either partly as sewage sludge, partly as fertilizer, or completely as mineral fertilizer.
Correct.
Okay.
Okay, thank you very much.
Thank you.
Bengt, you can have a look in the chat as well. There might be
I'll
some
do
other
that.
questions you can follow up on. And now we'll go on to the next speaker, which is Cinta Cazador from Fertiberia in Spain. One second. Cinta is working in Fertiberia, and she will tell us about the specific use of recovered vivianite as a fertilizer. Please, Cinta, the screen is yours.
Okay, good morning. My name is Cinta. I'm going to the specific case of recovered vivianite as a fertilizer. We are very happy and thankful to ESPP because we always love to talk about this great example for us of circular economy, which is vivianite. This is one of the pillars of Fertiberia, as well as the sustainable agriculture that we to promote every time. So before starting with the agronomic trials we have performed for all these years, I would like to point out that all the vivianites that we have used in these experiments have followed the methodology described in the European patent owned by INRAE, which is a company that belongs to Fertiberia Group. And this methodology claims that we can use almost any liquid stream with phosphate that can come from treatment plants, fertilizer industries, phosphoric acid plants, even gypsum stacks. So any liquid stream with phosphate is acceptable to use with this methodology. So starting with the agronomic trials we have performed, processes, especially in Mediterranean soil, which have different high pH. And in those soils, the iron is not blocked. It affects to a very important crops such as olive trees, vineyards, or fruits such as peaches, pears, etc. So this is very important in the Mediterranean area, and that is why we try to develop this product following this methodology. This trial that you are seeing was made in cucumber in 100% calcareous sand to see the effect of our vivianite compared with the usual treatment that a farmer or a gardener can use, which is the iron chelate. You can see in the pictures and in the table that at the end of the trial, there were no significant differences between both treatments, between our vivianites and between the iron chelate. Both in the pictures, you see those are healthy plants, and those are the symptoms of iron chlorosis. Green nerves and leaves light green or even yellow. This is related to the SPAT index. The SPAT index is a measurement that is related to the chlorophyll content, and the chlorophyll content, as you can see in the picture, is related to iron chlorosis. So there were no differences between the iron chelate and our vivianites in terms of SPAT index and in the plant growth. The plant growth was similar. So the vivianite was efficient in this sense. And after that, we developed a technology to incorporate the vivianite in the NPK fertilizer matrix. That is that every granule of fertilizer contains vivianite, contains the iron of vivianite. So we compare one conventional fertilizer from Fertiberia with this new fertilizer, also in pot trials, in pepper in this case. We tried 3 different dosages of every fertilizer. And again, we realized at the end of the trial that both the biomass, the final biomass, and the SPAT index were higher in the case of the NPK with vivianite. Here we have to compare the same dosages. So T1 versus T4, T2 versus T5, and T3 versus T6. In all cases, the NPK with vivianite released better results than the NPK without it. And the same thing happened with the SPAT. The green lines are the numbers related to the NPK with vivianite. So, but what happened, this was made in control conditions, but what is going to happen in real environments? What is going to happen in the field where we think we can control anything? So we designed a 5-year trial, long-term field trial. We chose the same plot and we applied the same treatments in the same experimental unit every year. We compare a usual NPK fertilizer, 8-15-15, with 8-15-15 with different amounts of vivianite. You can see here, look at the soil. There are very, very poor soils, very calcareous soil. It is almost white. So to see really the effect of the iron chlorosis is if it is possible. And we realized again at the end of the trial that in both the crop yield and the SPAT index, the NPK with vivianite released better results than the usual NPK. Every year, well, here it was the same, it was similar in wheat, but in the rest of the year, we had better result with NPK mixed with vivianite. I would like to point out that in the last year here in veg, we did not apply any fertilization here. We wanted to see, because, well, veg is a leguminous plant that knows how to uptake the nutrients, so it really doesn't need a lot of fertilization, or it doesn't directly need no fertilization. And we took advantage of that to see the effect of the long-term vivianite that we applied during the previous year. As we have mentioned before, or it has been mentioned before me, the phosphorus that is in the vivianite is not water soluble, but it is available for plants. So when the plant needs it, it takes it. So it is what happened here in this last year, and that is the reason of this phosphorus and iron uptake in this last year that came from the previous year. So this is a vivianite is also known as a slow release fertilizer because of its low solubility in water. So this can be the reason for that. And finally, this is another example of the efficiency of vivianite in the south of Spain in wheat. Here, the common practice of the farmers are the application of diammonium phosphate. I mean, NP fertilizer, diammonium phosphate, or another different, but mainly DAP. And we try to compare them with vivianite plus an extra addition of nitrogen to have the same fertilization units. And we also realized here, we saw that the best treatment, both for the kilograms per hectare of grains of wheat and also for straw, compared with for us, the positive control is DAP, but all of them are a positive control, we can say. So this vivianite with nitrogen was the best treatment among all of them. So we have demonstrated both in controlled conditions and in field, in real environment, the efficiency of the vivianite developed by this methodology and the efficiency of the NPK mixed with vivianite with the novel developed technology by Fertiberia. So yeah, we strongly believe in this kind of compounds And this is all from my side. Thank you for your attention.
Thank you very much, Cinta, for these examples from Spain. Chris, do you have some questions from the audience for Cinta?
There are some questions about if you can go back to slide 3, which shows different biomass productions. It's between the difference between T3 and T5. If you can explain that. Can you put the slide, Sarah?
Is it? Can you see it?
Sorry, it's not being shared.
Okay, sorry.
Okay.
I'm going to share
Can you
again.
share your screen again?
Yeah, of course. Sorry. Yes. Here. Is it? Slide 3.
Yes.
So which is the question, sorry?
Can you explain the difference between T3 and T5?
Well, T3 and T5. T1, T2, and T3 are all NPK 2612. And T4, T5, and T6 are 17, 8, 10. The differences are the NPK and some secondary nutrients and micronutrients that there are. I think that and 3 different dosages calculating by the nitrogen content. Can you see that? All treatments have the same, almost the same, more or less, you can say the same nutrients. The differences came because, well, all of the 2 fertilizers had boron, but the first fertilizer contained magnesium, but the second one doesn't contain magnesium, but it contains iron and zinc. This is because this is something in a commercial point of view, because this was, or this is fertilizer, common fertilizer in Fertiberia, and we try to redesign it in pod trial to this one. We decreases the total units of main nutrients in 3%. So this has less nitrogen, you can see that, but it has 2 more units of phosphorus, but it also has less potassium. And despite that, the results were better. So it's a combination of this redesign of main nutrients and the addition of iron and zinc. But we don't have magnesium here, and we have magnesium here. So this is those are different concepts. But in the end, we believe in the substitution of this treatment developed by Fertiberia for this new one. The differences are the nutrients and the dosages, actually.
Okay, thank you. Another question, do you have any data on the phosphorus contents in the plant material?
We have it, but we have not exposed them, but we have it, of course, yes. But we have to check it. It's just for summarize. Yeah, we normally measure all the main nutrients in the leaves, in the soil at the beginning, at the end, sometimes even in the roots, and also micronutrients, secondary nutrients in the leaves or in the grains, in the fruits. So those are normal practices that we do in our field trials, of course, and in the pod trials to know what's happening. Yes, we have it, sorry, but I have not shared it because of the time. I have to.
Okay, right. And there are a number of other detailed questions about some of the data and the nutrient balances, which you've partly discussed. I think one fundamental question maybe is, this is on calcareous soils. So are we talking only about a certain type of soil which is effectively lacking in iron, or is this something which can be generalized across a lot of soils?
Well, in acidic soil, there are soils that are not iron deficiency because it's available for the plants. So the challenge here, and also the phosphorus, the challenge here is in the Mediterranean soils that, you know, high calcium carbonate content, high pH. So normally when we try to to correct or to prevent the iron chlorosis, if a farmer adds, for instance, iron sulfate, this iron, as it goes in the soil and it is dissolved, it's very quickly precipitate as, for instance, ferric phosphate. I was very surprised for the results for my previous colleague, but it is normally not available, this iron. So this is a, let's say, cheaper way and also sustainable way of adding iron in the soil in this kind of Mediterranean soil in which the iron is not available for plants. The vivianite had this particularity that is not water soluble, so that helps in the solubilization of the iron little by little. Of course, this iron, as vivianite, is absorbed by the plant because the phosphorus in vivianite is available for the plant. It is soluble in neutral calcium, in neutral ammonium citrate, so it's available for the roots of the plants. So as the plant starts to absorb this phosphate in the vivianite, the iron is released in the soil. But this iron can be also absorbed by the plants, or it is oxidized. Of course, what iron wants always is to be oxidized. So, but this oxidization that takes place in the iron from vivianite, it is done in amorphous phases, in amorphous forms, not crystalline forms. So the plant is able to absorb it. That is the key in vivianite. That is why the vivianite is special for that. That is the reason. But the problem is mainly in calcareous soils, in the Mediterranean area, not in the acidic soils. No problem with iron there.
Okay, so you're basically saying that you include it as vivianite in the fertilizer and it stays as vivianite in the soil, and
Yes.
then only changes to amorphous iron, whatever it is.
The iron, yes.
When the plant roots effectively attack it to get at the phosphorus.
Yes.
Okay.
Yes.
I think that covers everything.
Perfect, thank you. Please, Cinta, also take a look in the chat if there are some other questions that you can address.
Yep.
Thank you very much. Sorry.
Just one comment to everybody, please. Please, can you use the chat? I've no idea what that, it's conversé in French and it will be something else in other languages, and not the question response or question and answers, because for technical reasons we can record the chat, which means we have a record of it and we can therefore retrieve your questions afterwards and make sure we answer them. Whereas in the questions and answers, they seem to get lost after a certain time. So please use the chat function rather than the questions and answers. In the bottom of the screen, the chat function should be to the right of questions and answers. If it's not visible, press the little dots that say more.
Okay, perfect. So we'll move to the next speaker, Kees Langeveld from ICL, who will be representing Fertilizers Europe today. So Kees has long experience in the fertilizer industry and has been active in many circular economy projects related to recovery of phosphorus from struvite, sewage sludge ashes, and he has also been project manager for projects such as RecoFos and Tenova. So I will share your screen now, share your presentation now, Kees, so that you can go online.
Yeah, thank you,
Okay,
Sarah.
is that all right?
Everybody. I want to say something today on behalf of Fertilizer Europe. Fertilizer Europe is the organization for fertilizer producers in Europe, located in Brussels. For decades, the fertilizer industry has already been, next slide please, has already been active in using byproducts from...
Kees, you need
Yes.
to speak closer to your microphone, please.
All right. So for decades, the fertilizer industry has already been using byproducts as raw materials for its fertilizer production. A few examples well known are ammonium sulfate from caprolactam production, sulfuric acid from various processes. So recycling and circular economy is actually not new to the fertilizer industry. Since the last decade, circular economy is getting much more attention also in Brussels, and it is something that we cannot escape from, so we better join it, is the idea in the fertilizer industry. In order to do that also in practice, I can show you some examples of what was done already. Some project looking at using biogas as a source for ammonia production, using sewage sludge ashes and meat and bone meal ashes to substitute phosphate rock in NPK or PK production, using struvite from water treatment plants into various products, participating in manure processing projects where the fertilizer industry can be a partner in order to release local farmers from excess quantities of nitrogen and phosphate and keep the organic material on the farm, etc. Iron and phosphate are used in different formulations. Cope with iron deficiency, it has already been mentioned by Cinta, the iron chlorosis, and also as a kind of a fungicide for musculus. Next slide, please.
Kees,
yes.
You need to face to your right, then we can hear you. Your microphone must be on your right. When you face left, we can't hear you.
Okay, thanks for the tip. Where can we use iron phosphates into the fertilizer industry? You heard already today some places where research is being done on use of vivianite and other forms of iron phosphates into fertilizers. More is going on several other places. The problem, of course, is that vivianite is not water soluble by itself, so you have to give it some kind of a chemical treatment to make it water soluble. You can argue whether it is plant available or not. I think to a big extent, even vivianite and iron phosphates are plant available. But normally you are looking for, in agriculture, a combination of rapidly available water soluble P and plant available P, and even in some cases to controlled release long-term available P. Several ideas are being worked out at the moment, and soon there will be some more concrete potential projects starting up. It depends very much how effective the vivianite technology as a reducer of phosphate in effluent will take off. If that technology is really, and it has good chances because of the good efficiencies it can prove, if the technology is taking off, I want to give the message that the fertilizer industry is ready to have a look at closing the circle and trying to use vivianite or similar products somewhere in their production system for fertilizers and bring it back to the soil again. Thank you for your attention.
Thank you, Kees. I think we have a couple of questions from the audience. Chris, did you pick up some questions for Kees?
This microphone is off, Sarah.
Oh, sorry. Chris,
sorry, no, it's my fault.
You were mute.
Sorry, my fault. Yes, there's some discussion about the solubility and the availability of vivianite. And if you're using vivianite in the fertilizer industry, maybe how do you ensure that it stays as vivianite when you deliver it in the product?
you have to do some research on that, and sometimes it could even be helpful if during the production process the vivianite is going to be modified a little bit to be more plant available. Those kind of things have to be researched and proven into agronomic tests what is really happening there.
Okay, I have another question to the different speakers. Is there a risk of toxicity by using vivianite in more acidic soils? Or toxicity of iron to the plants?
Well, I can say something about that. Unlikely, and it's toxic under reducing conditions where the iron is reduced to ferrous iron. So it has actually quite a serious constraint in rice production in highly weathered iron-rich soils. But I'd say very unlikely in aerobic soils, even with large amounts of vivianite.
Okay, and maybe a last question to Kees. Roughly how much vivianite could the fertilizer industry potentially use?
You would be talking about, it's a wild guess, but I think it's something like in terms of iron, it will be around 5,000 tons, first guess.
So 5,000 tons of iron.
Yes. So you could talk about substantial quantities, in my opinion, compared to what comes available.
Okay.
Thank you. Thank you very much for that, Kees. Please have a look in the chat where discussions are ongoing, and please chip in there. So next speaker is Antonio Delgado from Sevilla in Spain. Antonio is professor of agronomy, and his research is focused on soil fertility and fertilization management, and the interaction of organic matter and microorganisms with plant nutrients. Antonio is also part of the P-TRAP project that has been co-organizing this workshop with us. So please, Antonio, can you put your screen in slideshow mode, please?
Now, good morning, everybody. I think that the presentation is now available for you. It's okay? Sarah, can you see the presentation, my presentation? Is it not shared? Yes.
Yes.
Sure. It's shared. It's, okay. Hello, good morning. We have some experience working with vivianite, synthetic vivianite, because as Cinta has mentioned before, this is an efficient iron fertilizer for overcoming iron chlorosity deficiency in calcareous soils. So in Mediterranean areas, calcareous soils are frequent, are standard, so this is an important agronomic problem for sensitive crops. So we have clear evidence about its potential for overcoming iron chlorosity deficiency. It's efficient, and also it has a high residual effect. So in fruit orchards, vivianite can be effective controlling the problem during 4-5 years. In this term, you have to apply at least 12-15 times iron chelates. So there is a big difference in the residual effect, and also there is a big difference in the price of the fertilizer, because vivianite can be quite cheap, even if you produce from ferrous sulfate and diammonium phosphate. However, perhaps evidence about the potential role as P fertilizers are not so abundant. We don't have clear evidence about this in Mediterranean soils, and in particular in calcareous soils. So, but we have to think how plants can use, and the evolution of the vivianite in soils, to think how phosphorus can be used, phosphorus from vivianite can be used by plants. The effectiveness of vivianite as an iron source depends on its slow dissolution, but also on the oxidation products that are very poorly crystalline iron oxides that are known to be an iron source for plant in calcareous soils. This evolution is affected by the release of phosphorus from vivianite, and also the disruption, the dissolution, and probably the oxidation of vivianite in soil is affected also by P uptake by plants, P from vivianite. So this affects the dissolution rate probably, and also is going to affect the oxidation products. Which are the limitations probably? It has been mentioned before, solubility. Solubility perhaps is a problem for application of the fertilizer. It's very easy to apply a soluble fertilizer. It is going to be distributed on the soil if you apply granules to the soil. But the problem with vivianite to be effective as an iron source and perhaps as a phosphorus source is that it has to be located close to the root system of plants, just to enhance the dissolution through the mechanism of the roots for mobilizing nutrients, including irons. So this solubility is going to affect and probably to limit the application methods of the fertilizers. On the other hand, this solubility might be perhaps an advantage for a long-term residual effect. So this means that there is a slow release of iron, but also slow release and a slow mobilization by plants, but probably also a slow release of phosphorus. And one has to wonder if really in calcareous soil where there is a fast precipitation of non-soluble calcium phosphates, this slow release of P fertilizers is going to promote the absorption of iron oxide instead of a fast precipitation of insoluble calcium phosphate. So perhaps this slow dissolution, this low solubility is going to affect also the efficiency of the phosphorus supply as vivianite. As an evidence, sorry, I have to change the slide. This is a quite old experiment with my group about the oxidation of vivianite, and which is the product that we can have from the dissolution and precipitation of iron from this vivianite. That is a poorly crystalline iron oxide that is an effective source of iron for plants also. But the precipitation of the lepidoxide is going to be conditioned by the P concentration around the granules and the particles of vivianite. This experiment was performed with a removal of phosphorus simulation, with a simulation in order to mimic the behavior in the rhizosphere where plants can take this phosphorus and what could be the product of this dissolution and precipitation of vivianite, that in a calcareous soil or a soil with a basic pH is going to be a slow process with a slow release of nutrients. Okay, thank you very much.
Thank you very much, Antonio. Chris, do you have some questions from the audience for Antonio?
There's a question for clarification about so you're saying that effectively it's the oxidation of vivianite in the soil which releases the phosphorus and releases the iron. So that applies to iron 2 phosphates and not iron 3 phosphates. Can you clarify that?
Sorry, please clarify what I understand.
You're talking about the oxidation of the vivianites.
Yes.
The question is, does this imply that it's crucial to apply iron 2 phosphates and not iron 3 phosphates to soil?
Okay. Okay, there is a difference that iron 2 from vivianite is going to be also a source of iron for plants. The problem for iron chlorosis deficiency is that iron 3 doesn't move across cell membranes. So it's going to be more effective a source that is going to release slowly iron 2. The other side is that this iron 2 is going also to precipitate, to oxidize, and to form poorly crystalline iron oxides. These poorly crystalline iron 3 oxides are going to be mobilized are going to be used by root mechanism mobilizing iron, taking iron from these oxides. So this is a double, probably a double effect. The first effect, that is a dissolution of the iron 2 phosphate, that is going to supply probably phosphorus and iron 2 that is going to be moved, that is able to move through cell membranes, but also the production, the precipitation of iron oxides that are also a source of iron, but also, this is something that we have to study, also there is a possibility of acting as a p-sorbing surface.
Okay, so you said it was important to apply the vivianite near the plant root.
Yes, it's poorly soluble and it's not going to move. Iron and phosphorus are not going to move in the soil. So you have to make a banded application or allocate application close to the plants just to facilitate the use and the mobilization also of the vivianite and the products formed from vivianite, the mobilization through root mechanisms like the ion exudation or acidification by roots. But the effective application is just to band close to plant roots.
Okay, and maybe a question to come back to the previous presentations. If you're effectively applying iron phosphate not as vivianite but as iron phosphate in sewage sludge, is this the same uptake mechanism or a different uptake mechanism? Is there a link between the two?
Well, there are two questions here. One is that probably these iron phosphate are not going to be thermodynamically stable, so stable in calcareous soils, but the iron is iron 3, and the problem with iron 3 in the first release is that it's not so effective like iron 2. On the other hand, probably this iron 3 is also going to precipitate as poorly crystalline iron oxides. This poorly crystalline iron oxide precipitation is affected, is determined also by a relatively high peak concentration close to iron particles, because this phosphorus is going to enhance and to decrease, sorry, the crystallinity of the precipitation products. So probably it's going to be a sort of iron, but I think that less effective than iron 2 phosphates.
Thank you, Antonio. I think we'll move to the next speaker now, Erik Smolders from the Catholic University of Leuven, who will tell us about iron in soil and plant phosphorus availability. So I will share your presentation here. Can you see it all right?
Okay, Sarah, can you just confirm that you hear me clear and loud?
Yes.
Okay. So welcome everybody. I'm going to talk about iron in soils and plant phosphorus availability. It's not about iron phosphate as a fertilizer, but the iron in the soil. What is the role of iron in the soil? Next slide. This slide here shows an extreme, probably the most extreme field I've ever encountered, where phosphor deficiency is so large that you cannot grow any crop. For 3 years, we have been growing rice genotypes in Madagascar in a highly weathered soil that contains very large iron concentrations. We added nitrogen, potassium, we added water, we added efficient genotypes, but we had repeatedly crop failure compared to the complete NPK fertilized soils. So we needed high doses of phosphor to obtain good yields, and without phosphor, with all the other nutrients added, we had a complete zero growth. So if you want to have response curves in a linear line with no intercept, that's the place to be. And we called that field also the iron mine. Next slide, please. Just to take you back a bit to your textbooks of soil science, when soils develop over time during soil weathering from parent rock to current soils, in the beginning, you have the nitrogen that is a limiting factor. In very, very young soils, you have no nitrogen. I'm talking here about natural soils, not agricultural soils, but under normal development, the pioneer vegetation has some nitrogen fixers and it will gradually bring in nitrogen. In the beginning, you have nitrogen limitation. However, when the soils are weathering and all the minerals are weathering, you have less and less available phosphor. Not the total P is decreasing, but the availability of phosphor is decreasing. And that is because the young minerals, they have reasonable sources of phosphor, but the minerals that are associated to weathered soils are typically the least soluble minerals. These are the iron oxyhydroxides and aluminium oxyhydroxides. And they scavenge the phosphor and bind it so strongly that you have very limited phosphor available. And that is the reason why in highly weathered soils and old soils, that phosphor is the main limiting factor, also explaining the high biodiversity we often find in tropical rainforest, where phosphor is the limiting factor, controlling the high biodiversity. Next slide, please. At the origin of the low phosphor availability in high iron soils is depicted here. Iron is present in octahedral configuration with oxygens in, for example, goethite or ferrihydrite, different iron minerals. And when you have two adjacent octahedra, you have these on the tops of the outer surface, these two oxygens that can form a ligand binding, well, an inner sphere binding with a phosphate molecule. Here you see a phosphate that is bound bidentate to such an octahedral, two octahedra, so the corner sharing octahedra. And that phosphate is so immobilized that it is not soluble and not available for the plants anymore. Next slide. An illustration of that is we collected a series of soils in highly weathered environments. So that's typically in old continents where it's wet and warm. And from a series of soils from Kenya to Madagascar here, we collected soil samples, characterized them in the lab, and they are sorted here by increasing concentrations of polycrystalline iron, the oxalate iron, Fe-ox, so sort from low to high. We grow plants on it, and we first did a soil chemical characterization. How much phosphor do we have to add to that soil to obtain 0.2 milligrams of phosphor per liter soil solution, which is about the adequate amount that you need in a soil to have sufficient plant growth. And as you can see in the last column, the phosphor PSI, the phosphorus saturation index, increases with increasing iron concentration from a very low dose required of 15 milligrams per kilogram up to an extreme dose of 1,000 milligrams. And it gradually goes up, some up and down. So that's soil, for example, from Kenya, Bokoli, needed a bit less, but that's also a less acid soil. It's not only iron, it's also pH that controls. But in general, the general picture is that you need in some soils extreme doses of phosphor to obtain sufficient plant growth. Just to remind you, 1,000 milligrams per kilogram of soil, that's equivalent to about 2 tons of P, not PO5, but P per hectare, which you need to apply in that soil, for example, in Madagascar, to obtain sufficient plant growth. Next slide, please. When we did pot trials with this series of soils, we had to add greater doses of phosphor and had dose response curves. And in the end, what we showed is that, in fact, for maize plant, that the yield increases are related to the phosphor in solution. Well, here measured with a DGT, it's just the phosphor, the soluble phosphor, and it saturates near when you obtain about 200 microgram P per liter, or which is close to that 0.2 milligrams of phosphor per liter soil solution. Increasing iron in soils require higher doses of phosphor to reach the same soluble P. Next slide, please. How to address that issue with highly weathered soils, high iron and lower phosphor availability? Well, it's not all that simple. There is, of course, more in soil than just iron and phosphor. The organic matter is a very important competitor. Again, here you see an iron oxyhydroxide. Now in brownish are all the octahedra. And the blue shades indicate an organic molecule. Here it's citrate as a model component for organic soil organic matter. So the polycarboxylates, so these anions, they also adsorb to the surface of the octahedra. That can be an inner sphere complex or just an anion attracted to the positive charge of the iron oxide. The result is that increased concentrations of organic matter at equal total soil iron will increase the solubility of P because it's a competing element. It's a competing element. It's not simple competition experiments because competition things, because many of these sorptions are irreversible, but the general idea is that increasing organic matter compete with increased phosphor. Next slide. And that is shown with that work that we did in Madagascar. For 3 years, we did repeated applications of phosphor, just a classic phosphor fertilizer experiment, all at the same N and K doses. And in year 3, you can see that in red line is just a mineral fertilizer response curve that we added up to 80 kilograms of P per hectare. And the uptake in the rice plants, the grain and the straw, was only 8 kilograms. So you add 80 annually and you get only 8 back in the crop. So that's 10% only of phosphor use efficiency. But when you add farmyard manure, organic matter, along with that phosphor, and you keep all the other nutrients balanced, and you keep the water balanced, etc., then you see that you have an equivalent phosphor dose, total P dose, P derived from farm manure and mineral, that you have a higher yield. And that can be explained by the effect of organic matter competing or blocking the phosphor binding sites. Next slide, please. 2 more slides to conclude about recent work. I guess most of you know that in Europe, we have a high stock of phosphor in our soils, a legacy, and that we need to use that soil P stock now, that we should let less phosphor and that we should mine the soils for phosphor. You can do that, you can use the stocks provided that the residual value of that phosphor is high. And when you have high iron in soils, that phosphor is not only strongly bound, but it's also irreversibly bound, especially when you have very high iron and low phosphor. Now, what we did is a study, but it's still ongoing, on the role of organic matter. The idea being that when you have high organic matter, the phosphor that is in the soil is probably more reversibly bound. We have a wide range of soils in which we do phosphor desorption curves, mimicking the phosphor, taking the phosphor out. So here, more than half a year desorption time. And when you have a high organic carbon over iron ratio, you have more phosphor and it becomes more readily available. So for example, after 1 month, we have about 20% of the oxalate extractable phosphor already desorbed. And then last slide. When we plot the labile fraction, what we call is the fraction that is fast available within a given amount of time, that labile fraction, and we plot that to the organic carbon over iron ratio. It's a molar ratio. It's not indicated here, but that's a ratio of organic carbon to iron in the soil. And we see that in soils that have only low phosphor availability, well, moderate, not saturated, that with increasing carbon over iron ratio, there is more labile fraction, there's more labile phosphor, so that organic matter keeps the phosphor more in the loop, whereas when you have high saturation, there is not such a large effect. So the conclusions that take home in the last slide, Sarah. So the last slide. So increasing iron 3 in aerobic soils enhances phosphate sorption and increases the need for higher fertilizer doses. And that's especially true in highly weathered soils where you need high dose of phosphor. Soil organic matter is key to keep phosphor available, and it lowers the need, increasing soil organic matter, it lowers the need for phosphorus equals soil iron. So the organic farming between brackets, just defined here as farming with higher organic matter input in the soil, it may yield better long-term P supply at equal total P input than when you only add mineral fertilizer. And with that, I conclude.
Thank you very much, Erik. Very interesting about the role of organic matter. Chris, I think we have some questions from the audience for Erik.
First question is, did you also apply micronutrients or only macronutrients in your experiments?
In the field trials, we generally do not apply micronutrients, but we monitor the leaves for micronutrients. We look at, for example, zinc, and by the foliar analysis, we know that there is no lack of micronutrients in these acid soils. Yeah.
Okay, and do you think these results about the importance of organics would apply also in less acidic soils?
To a lesser extent. It's of course that what we show is in fact extreme cases where you have very high iron and low phosphor. In most of our soils, when it's not as extreme, first of all. So we have in terms of the labile fractions, but we always have that confounding factor here in Europe. In the soils that have high organic matter, they often come from soils that received a lot of phosphor, so manure or sewage sludge and so on. Then we have a high phosphor to iron ratio already, where you have very little competition effect. You have to go to, in fact, low input systems to find more that effect of organic matter. So, of course, that is keeping phosphor in the loop is, of course, more important for these environments where you need these extreme high doses. I want to remind everybody about the phosphor doses that we applied in these fields. Years and years of 80 kilograms of P is an enormous dose of phosphor, which reminds us of the earlier development in Europe, where we sometimes also did these kind of things. Yeah, it's not like the 10 or 20 kilograms of P per hectare.
Okay, I have two other questions. One is, what is the role of the microbial activity in the organic matter? So is it purely chemical, or is it also related to things, microbial activity mineralizing the phosphorus?
There is, of course, an effect of mineralization but in the soil that we are studying, the iron concentration is so large that any phosphor that is released by mineralization is also immobilized. It's of course very well. What is the role when you do the estimates of phosphor mineralization? You end up with numbers like 0.5 kilograms of P per hectare per day is a very high value already, and the phosphor that is released, do not forget, under these conditions, is immediately also scavenged. It's extremely, in these soils, it's also extremely difficult to measure phosphor mineralization. At the same time that phosphor is released by mineralization, it's sorbed and immobilized. So you need to do all of these isotope-based techniques to identify the mineralization. So in fact, we cannot quantify it exactly, But we expect that the effect of mineralization in these conditions is quite limited in high iron soils. It's completely different, of course, when you compare that to an organic soil or peat soils or forest soils where the mineralization keeps the phosphorus in the loop. Yeah.
Okay, maybe one last question. Are there any interactions with sulfur?
There are, but they're moderate. The sulfate-phosphate competition is clearly in advance for phosphor for sorption. There is a competition, but it's little. Yeah.
Thank you. Thank you very much, Erik. You can follow up also in the chat where there might be some other questions as well. We'll go to the next speaker, Kirk from Cranfield University in the UK. Guy is professor of soil systems with 30 years of experience in the biochemistry and modeling of soils and plant-soil interactions. He has spent 13 years at the International Rice Research Institute, and currently it's working on projects including mechanisms and genetics of iron toxicity in African soils. Please, Guy, the screen is yours.
Good morning. Thanks very much, Sarah. Are my slides visible?
Yes, can you go to, what is it called again? Slideshow mode. Yes, there, perfect. Thank you very much.
Good. Well, I'm going to talk about how roots extract phosphate from just the sorts of soils that Erik has been talking about, the highly weathered, iron-rich soils where the phosphate is extremely insoluble, and particularly the role of root-induced changes in the soil in allowing plants to get their phosphate, and how we can investigate those processes using mathematical modeling. And I'm going to use upland rice as my case study. Upland rice grown in unflooded soils, not paddy rice, so rain-fed, unflooded soils where phosphorus is often the major limitation, and particularly in these highly weathered iron-rich octosols and ultisols. And some varieties of upland rice are very efficient in extracting phosphate from these soils by mechanisms that are not entirely well understood. But my colleague Matthias Wasua, who is a plant breeder in Japan, has worked on this for some years and has identified upland rice varieties which differ many-fold in the amount of P they can extract under given conditions. And he's gone to some extent in identifying molecular markers associated with traits for mechanisms allowing upland rice to tolerate these conditions, and some understanding of the genetics involved. But the mechanisms remain not so understood. And broadly, these are the sort of possible mechanisms, and they divide into mechanisms internal to the plant, so allowing the plant to grow and yield more for a given amount of P taken up, versus external mechanisms which allow the plant to take up more P. And there's obviously an interaction between those two. More P a plant has, the more scope for exploiting internal mechanisms. So there's a bit of a chicken and egg in resolving those two. But of the external mechanisms, Matthias has shown that root geometry effects are certainly involved, and particularly upland rice varieties with a higher proportion of very fine laterals covered with long root hairs, so long rather than dense. So hairy, fine laterals are good for P uptake. However, mycorrhizas do not appear to be involved, although in general, upland rice growing in these conditions is mycorrhizal, and the root surface is thereby greatly extended. Differences between genotypes, varieties of rice, in P uptake aren't related to differences in mycorrhizal activity, and that's been shown quite clearly with experiments. And nor is the root absorbing power, so the ability of a root to suck up P from the soil for a given concentration at the root surface. Models show that roots essentially behave as zero sinks for phosphate in these conditions, and better transporters don't make much difference. So there is some involvement of root-induced changes in the soil that make the phosphate more soluble. The roots don't just behave as passive sinks. They modify the soil in some ways that make the P more soluble. This talk is mainly about that. So I'm going to start with some really early work, 25 years old, I've just realized, in which we grew upland rice varieties in little pots separated from a lower pot with a mesh. So the fine roots could not penetrate the mesh, the hairs could, but it meant we could then section the soil in the lower pot parallel to this planar layer of roots on the mesh, and look at what pools of phosphate and other root-induced changes had the plants had caused. And in this system, again, the mycorrhizas weren't involved. And what we found was this: on the left shows the soil with no P, and the right with a little bit of P added. There was no P in readily extractable forms, so what we could extract with a resin or with a bicarbonate solution. Most of the P was in forms that you needed quite a strong extractant to get at. So here, 0.1 molar sodium hydroxide, and the P added mostly went into that pool, and most of the P taken up by plants came from that pool. So this tells us that the plants had to work pretty hard to get their P, and they did something that allowed them to get at this alkali soluble pool. Well, our first idea was this might be some sort of exudate from the root, a low molecular weight organic acid or anion, such as citrate, which, as Erik showed, can make phosphate much more soluble. And we had found in other experiments appreciable concentrations of citrate in particular around upland rice roots. So we did some modeling to find out what sort of rates of citrate excretion would be required to account for the measured uptake, and were they, could we actually find those in upland rice? So here's the model. Here's the basic model, which shows diffusion of phosphate through the soil to an absorbing root. So here the root is just a passive sink. It's taking whatever P it gets from the soil solution, where it's mobile, close to the surface, and then is replenished by diffusion. And we can show with this sort of model that however hard the root worked, it wouldn't get anywhere near the P it required. And then here's a model in which we add in the potential effect of a root exudate such as citrate. It's diffusing out from the root, it's being decomposed by microbes, and then it's reacting with the soil and making the phosphate more soluble. And note, the solubilized phosphate can diffuse towards the root, but it can also diffuse away. So a neighboring root can actually benefit from P solubilized by the original root. So there's a possibility of an interaction here with the root geometry. Anyway, so we can model all those processes and measure, independent of our phosphate uptake, all the parameters involved. And here are some results of that. These are the concentration profiles of phosphate in our root plane system, what I showed earlier. Depletion of phosphate after a week, 3 weeks, and 35 days. Depletion of total phosphate, profiles of citrate moving away from the root, and then the increase in phosphate in solution. Again, the parameters involved in these calculations were measured independent of the uptake. So this sort of suggested maybe the citrate mechanism was viable. However, when we went back to look at in more detail how much citrate was released from roots into nutrient culture, we couldn't find anything like the rates required, and we couldn't crucially find the difference between tolerant and intolerant genotypes in the rates of uptake. So we sort of went back to the drawing board with this, and our next mechanism was the possibility of pH changes solubilizing phosphate. Well known that roots in general alter the pH around them, and the pH change may be up or it may be down, and it's largely determined by the form of nitrogen take-up. If the nitrogen is taken up as ammonium, roots take in an excess of cations over anions, and they must balance that electrically by releasing protons. So this will acidify the soil, and in some cases that may solubilize phosphate. So in calcareous soils or in temperate soils with permanent negative charge, in which the phosphate may be bound to the surface via divalent cation bridges. In those sorts of circumstances, acidification may make the phosphate more soluble. But that generally doesn't work in the sorts of high iron, highly weathered tropical soils we're interested in with upland rice, where the charge on the surface is pH dependent, which means acidifying the soil may actually make things worse, may increase the positive charge on the surface and the binding of phosphate. Whereas an increase in pH, making the soil surface more negative, may solubilize phosphate, and that's the general finding, that increasing pH will make the phosphate more soluble.
You have 1 minute left, Kees. So
okay, I will accelerate. So we use modeling to look into this. How much might rice roots alter the pH? And to cut to the chase, they may do it quite considerably, and how much for a given release of base bicarbonate from the root, its effect is much larger depending on the pH. And we could include all that in a model and its effect on the solubility of phosphate, as for citrate, measure the parameters independently, and we found we could account for measured uptake with this mechanism with solubilization, nowhere near enough without solubilization. So here we think we have a mechanism which can account for our uptake by the tolerant genotypes. And implications of this, well, it may be a specific tolerance mechanism. Perhaps the genotypes know how to adjust the pH in their favor, but it may just be an indirect effect of better growth in the tolerant genotypes. But what it doesn't mean is there's a potential for manipulating this mechanism by manipulating the fertilizer formulation applied. So perhaps nitrate forms of fertilizer may encourage pH increase and solubilization. So this opens up a world of possibilities for exploiting genotype differences and management. That's it. I'll end there.
Thank you very much, Kees, for these examples. I'll stop the sharing. I think we have a couple of questions from the audience. Chris.
Yes, I'd like to come back to this, your final point about the form of the nitrogen in fertilizer impacting phosphorus uptake. So can you just clarify that again? If I understood correctly, nitrate will tend to cause a pH increase, and that would make phosphorus less available, is that right? Whereas an ammonium type fertilizer, such as MAP or DAP or struvite, would mean that when the plant takes up the nitrogen, it causes a soil, an acidity in the soil, a release of H+, and that might make phosphorus available. Is that a correct summary? And is that true in all soils or only in the specific soils you're looking at?
Well, a few things here. So in these sorts of highly weathered iron-rich soils with pH-dependent charge, the general rule would be a pH increase would make the soil phosphate more soluble. So a nitrate-fed plant might be able to, might solubilize phosphate. So that's one point. But how the specific phosphate fertilizer formulation affects things will also depend on how nice the environment around the fertilizer is for root proliferation. So you want, on the one hand, a fertilizer that doesn't make its local environment too toxic, too alkaline, or too acidic, or too high in phosphate locally for roots to be able to proliferate. So that's one aspect. You need to get the fertilizer formulation right to allow the roots to proliferate. And then maybe you can also manipulate the combination of fertilizer to solubilize the phosphate once the initial reactions are complete. So it's a complicated story, but potentially there are options to get the chemistry right.
Okay, do you want to say something on that, Antonio? I can see that you've been making long comments on the chat about pH and oxidation. Or Bengt?
Well, the oxidation of iron is easily done at a neutral pH, but and in an acidic environment, it's much more difficult. Considering the nitrates, I'm just thinking of the wastewater treatment where you increase the pH when you have the denitrification, but I suppose it's a different mechanism in the soil, so that hasn't the same influence on the soil pH.
So it depends both on whether the soil is aerobic or anaerobic and on its pH, as well as on iron and phosphorus.
It could have an impact, I would assume. I just wrote an answer also for one of the comments about the solubility of ferric phosphate and so on. And what we see in sludge is that it's not. It is a precipitate. It's not an adsorbed iron to begin with. So it is a salt, and normally that is transferred into vivianite when it's stored, and that can quite easily dissolve around pH 4.5. So in case you have acidic soils, of course, the vivianite is more available than if it's a higher pH.
Okay, and there were a number of comments relating to the form of iron phosphate, whether it's amorphous or crystalline. When it's in sewage sludge, it will tend to be which, and then what happens in soil, and how does that affect its plant availability? And indeed, what form will it naturally be in soil?
In soil, I can't say, but in the sewage sludge, it is predominantly amorphous to begin with. And then if it transfers into vivianite, it's more crystalline. I think Leon and WETSUS will talk more about that later on.
And in soils, maybe Ruben or Erik or Guy, is the iron phosphate more amorphous or crystalline, and does that affect its availability to plants?
I'm willing to answer this, Erik here. The majority is amorphous, as generally when soils weather, they get slowly into more crystalline. So the ratio amorphous to crystalline goes in the favor of crystalline when the soils weather more. And crystallines have typically a lower specific surface area than the amorphous. The amorphous ones are the ones that are typically used for phosphate sorption prediction because the specific surface area is so much larger. For the amorphous fraction, there we talk about 600 square meters per gram. And then for the crystalline, it's an order of magnitude lower than that. And the amorphous is, well, the traditional method to discriminate both is not by XRD, but it's just by an extraction, is the ammonium oxalate extraction, which is the Schwertman extraction of the 1963 paper still. That method is used to identify the amorphous iron and aluminium. And they are the most reactive ones in soils. So that's the reason why ammonium oxalate extractable iron is a good predictor for phosphorus sorption and not the total iron or what we call the DCB iron, the dithiamine citrate bicarbonate extractable iron is a lesser predictor. That's the specialists are in Spain for that. And a colleague of Antonio José Torrent is a specialist for doing all that work.
Well, another interesting case is volcanic ash soils, where there may be iron and aluminium in short order crystalline forms with extremely high surface areas, and even worse than these high iron ultrasols and oxasols in the tropics. And there it is crystalline forms which are absorbing the phosphate, but they have this extremely high surface area.
Thank you very much. Good. I'm happy to see the discussions going on in the chat, and then we can follow up with some questions. I think we'll go on with the next speaker, which is Ruben Sakrabani from Cranfield University in the UK. Ruben has a long experience in determining nutrient dynamics in soils associated with application of organics such as compost, manure, sewage sludge, and so on. I will share your presentation, Ruben, just a minute.
Yeah.
Okay, and I will put it to full screen. I think it displays correctly now. So please, Ruben. Oops, sorry.
Okay, thank you. Good morning, everyone. Thank you to ESPP for this opportunity to present this work. Can everyone hear me clearly?
No.
It's a bit of a bad connection,
yes,
I think, but please try.
Okay, right. Okay, I'll do my best. So yeah, this is to hopefully complement the previous speakers. The two slides that I will present following on will be just focusing on the role of phosphorus analytical methods and their implications for evaluating phosphorus availability in crops. I would like to acknowledge the co-authors, colleague Mark Pollard and master's student Benedict Hookwa, who also contributed to this work. Next slide, please. I think, yeah, just to set the scene, the use of chemical methods to extract phosphorus and indicate how available it is for plant has been going on for a long time. And just to kind of set the scene, the whole phosphorus availability in soils pool, and then obviously you've got the other more recalcitrant pools, controlling the dynamic of this soils in pool form, and obviously pH is one of the predominant factor that influences this equilibrium. So this table here makes an attempt. Yeah.
Ruben, your sound is not very good. Can you try turning your video off?
Okay, fine, I will. Yeah, okay, is that better?
I think it's better, yes. Thank you.
Right. I will try and repeat a little bit of what I said. So the whole soils in the world of soil science, the whole soil phosphorus availability based on the soil pool concept, and where the soil solution P, which is the one that plants get access to, roots get access to, is the smallest pool, and you've got the more recalcitrant pools of phosphorus controlling the equilibrium. And pH is one of the key factors that controls this equilibrium, which the resulting fact is that the soil solution P is always the smallest. So hence, the use of these analytical methods to mimic plant available phosphorus has been going on for many years. And this table provides a summary. It's not an exhaustive list of soil P methods, but it provides a range. Hopefully these will be quite common, for those who are familiar with this. Certainly in the UK, the Olsen P is very common. And the reason I have kind of listed these analytical methods is to start from the very acidic ones, which is Bray 1, right up to the more alkaline end, which is relevant for Olsen and Colwell. And in this case, for the acidic ones, you can see there's the presence of fluoride, which is important to enhance the desorption of phosphorus from aluminium-bound phosphorus, which is actually very strong. And this shows how this plays a role in making the phosphorus available using this particular technique. I think the key message here from this table is basically to show that these different soil phosphorus extraction methods work in different conditions. And obviously pH is one of the key factors that provides the optimum operating conditions for each of these extraction methods. There's no one method that it suits all. It all depends on the different context. And this table hopefully summarizes some of the key operating context and provides the boundary conditions where these extractants work best and how you actually infer how much of phosphorus that can be extracted from these different methods. So the next slide, please. How much of the next slide shows a table that shows the previous methods that I've listed in the previous slide, but goes on further to say, whilst we say that, or we indicate that the extractants extract phosphorus from the different, conditions which are dominated by pH is one of the key factors. This table shows what does it mean for plant available? So just because you can extract it using a particular extractant, be it sodium bicarbonate, etc., for Olsen and many other extractants, it doesn't necessarily mean it actually is available for crops. But this table goes further to say how you can indicate what is available from a chemical extractant point of view and link it to what plants actually utilize it to obtain what is known as the critical p-value, which is shown by the graph. It shows critical p-value indicates the p that is needed to get the optimum yield for a particular crop. So for example, in the first row for Olsen P, it shows for a critical p of 18 milligrams per kilogram, there was a relatively good correlation between what the plant, what the extractant can extract and how that indicates to what the plant actually utilizes to get the optimum yield. And the number of soil samples analyzed in this particular case was 336, and the correlation was relatively good. But that does not mean that's the case for all the other conditions. For example, there are, for Bray 1, which is second last row, you can see that the correlation was a little bit lower, but the number of soil samples were also much lower. So it shows that the again, it's very context specific. So when you're utilizing these extractants, whilst they do indicate, how much is available, you also need to go further to see how that links to what the plants actually use to indicate its optimum uptake for crops. So I think, in summary, I think what we would like to say is that the different methods that are available need to be used in the right context to indicate what is needed for the crop, and to consider as well the boundary conditions that are where it works best for its best uptake. Thank you.
Thank you, Ruben. Do we have some questions from the audience, Chris, or Ruben?
Maybe to come back to the question of whether phosphorus forms used as fertilizers need to effectively be soluble. There have been a number of questions about products such as iron phosphate or the specific form vivianite, which are less soluble. Is this a disadvantage because they're less immediately available to plants, or is it in fact an advantage because it means there'll be less risk of runoff? And Kees Langeveld was saying that they were the fertilizer industry was considering reprocessing vivianite to make it more soluble. And some of Bengt's studies were using fertilizers showing they became available over several months or even years. What is the importance of the fertilizer forms of phosphorus being soluble in water or soluble in different materials, and how does that impact their environmental risks?
If I can attempt, I can't necessarily say for vivianite per se, but I think in terms of phosphorus solubility, that's definitely a key thing, because it's the phosphorus soluble, which is obviously what's in salt solution, is the one that plants get access to. So definitely solubility is key, but I think we need to get the balance right to make it not too soluble, because then the plants only get access, need what they need, and then anything excess will then obviously become either, if they're in excess, they can get reabsorbed, become unavailable, or can also be a waste. So I think we got to get the balance right in terms of not making it too soluble.
Thank you very much. I think we'll switch to our next and last speaker, who is John Lloyd from the University of Manchester. Please, John, the screen is yours. You can share your presentation.
Thank you, Sarah. Can you see the slides okay?
Yeah, you might. Yeah, exactly. Perfect. You're in full screen.
Wonderful. Well, no, thank you, Sarah, for introduction and for the invitation to talk today. It's a talk that's a little different from the previous talks in this session, focusing on microbial aspects around ion cycling and links to the phosphorus cycle. My own personal interests have been on the anaerobic components of redox cycles for the metals. So I've worked over the last 20 years on dissimilatory metal reduction processes where microbes use metals as electron acceptors for anaerobic respiration. We've been interested in the mechanisms of reduction, so electron flow in those systems, environmental impact, and also biotechnological applications whenever possible, including making a range of sort of nanomaterials for a range of applications. Now, much of this work is focused on the ion cycle, hence the context for this work. So I was asked to talk a little about microbial cycling, particularly around iron and phosphorus. To be honest, we've done a lot on iron and not so much with phosphate linked in, but that's an area we're moving into now through PTRAP. So what I was going to try and cover today was some background on the processes around iron reduction, the mechanisms, how they could be optimized, just demonstrate you can scale up these processes if you're interested, talk about the mineralogical and geochemical constraints associated with iron reduction, say a small amount about the bioreduction endpoints, the impact of phosphate on these processes, and vivianite as a specific endpoint, given the interest to this group. So for those that don't work in the area, this is a very simple schematic showing a subsurface bacterium growing on an iron oxide, taking electrons from an electron donor, in this case acetate, passing the electrons to the mineral assemblage, reducing the iron, and in this case some Fe2s being solubilized, and there'll be changes in the mineralogy and geochemistry around the cell. Now that little panel there shows you what's happening at the cell mineral interface. These organisms are incredibly interesting because they're respiring an electron acceptor at the surface of their cell. Most electron acceptors that are respired tend to get into the cell where they're respired, but everything happens on the outside of the cell with these iron reducers due to the poor solubility of the Fe3. And you can see on the right electron transfer chains that take electrons to the surface of the cell, and also proteinaceous nanowires that take electrons further out into the mineral assemblage. Now, there's a broad range of organisms that can do this. I'm sorry the slide's rather blurry. It was from quite an old reference from Derek Lovely, a great pioneer in this area. The reference is at the bottom. That phylogenetic tree will obviously be bigger now, but it's just to illustrate the broad range of organisms that can reduce iron, and a particular model organism that's been studied in depth is this organism here, Geobacter. Now, this is from some of our own work, and here we were feeding the cells with labelled acetate, C13 labelled acetate, and visualising the uptake into the biomass when they're in direct contact with the iron mineral, shown there in red. So that just emphasises that these cells have really got to be in contact with the iron mineral, in this case to pass electrons to the mineral and respire. The dark blue cells that have not been able to respire and take up the labelled acetate in that experiment, visualised using the nanosims. There's some other images here showing these organisms in action at the top left. These are Geobacter cells, again growing on an iron oxide film. You can see those as the light blue dots, and some AFM images showing what's happening at the cell mineral interface where these reactions are taking place. Now, in the context of this work, we've been very interested not just in the process, but the minerals that form. So we've had a long-standing interest in looking at these organisms reducing metals, including top left, precious metals and platinum group metals to make catalysts, selenium oxyanions to make quantum dot materials. And top right, if you feed these organisms iron oxides or oxyhydroxides in culture, you can make lovely fine grain magnetite. Now this is the process that we use in the laboratory. So ferrihydrite plus the cells and an electron donor. Now in the middle of that figure you can see there's an addition of an electron shuttle to speed up electron flow from the cells to the ferrihydrite. That could be a humic material or something that cells secrete, such as a flavin, but that can speed up reduction dramatically, and you can make large quantities of this fine grain magnetite within a few hours. And much of our work has focused on engineering that optimally, putting dopants in to change magnetic properties for materials that you can use for catalysis and remediation. These are scalable processes. We've run these up to from simple lab incubations at the half-litre scale up to 5 and 50 litre scales with commercial partners. And that scales very well, very efficiently. And for applications, the most important point really is you've got to have cheap substrates. So obviously if you want to make materials that could be useful, you've got to use waste iron oxides or oxyhydroxides. And we've done a bit of work on that, including life cycle assessment studies. In this citation here, we were working on waste iron oxides and oxides from acid mine drainage type systems that you could transfer quite efficiently to magnetic nanoparticles, including magnetite. So this has led us into looking at, as part of the circular economy, other reduced iron mineral phases that could be useful, and we've become very interested in Fe2 phosphates through the PTRAP program. And there's a project now that's I'll talk about very briefly at the end in this area. The constraints that we have to work against, so really we're trying to optimize, you know, vivianite production in these systems. You've got to consider electron donors, and that could be hydrogen or a large range of organics, redox mediators, for example humics, so naturally occurring redox mediators, or secreted flavins, and the electron acceptor itself. Now, iron mineralogy is incredibly rich, as I'm sure we all appreciate. The amorphous forms, sort of very hydrite type materials on the left, very fine grain, poorly ordered and reduced quite efficiently and quickly. And as you become more crystalline all the way over to hematite, particularly when you've got larger grains of hematite, those are very, very difficult to reduce. So crystallinity is a key player. Also, the presence of other electron acceptors that could be used as well, or in place of the iron. These organisms will reduce lots of metals. So looking at the processes, we did a big study several years ago, Rich Cutting and others, looking at a range of iron minerals. And to the left, you've got the more amorphous forms. To the right, you've got going through to hematite in the middle and goethite. You've got the less, the more crystalline forms, which are reduced much more slowly. The blue bars without redox mediators. The red bars are with redox mediators, and you can see ferrihydrite with the blue bars are the most easily reduced. They typically go to magnetite. There's TM studies here showing that the hematite and highly crystalline goethites aren't really touched, but at the bottom, the ferrihydrite type materials are reduced, transformed very efficiently to magnetite in this example. And that was backed up with XPS studies as well. Right, so the range of minerals that you can form, we've talked about solid phase transformation, so from ferrihydrite reduction, typically in our studies in laboratory incubations, you go to magnetite. But you can go to other reduced forms, so vivianite and siderite can both be engineered in the laboratory. Siderite, if you've got high carbonate, low phosphate, and if you up the phosphate levels somewhat, you'll get to vivianite, the reduced iron phosphate. So you've got some capabilities of fine-tuning the system in culture. If you look at solid mineral transformations and add phosphate in, here I'm referring to literature. So Thilo's worked on this in the past, and also John Zakara's group. And the consensus is, as you absorb the phosphate to the iron oxide or oxyhydroxide substrates, that will impede reduction and reductive recrystallization of your endpoint. So in these examples, phosphate can slow down and alter the trajectory for iron reduction. But interestingly, when you look at real world systems, so we heard yesterday about reducing systems where vivianite forms naturally in coastal and other marine systems. And this is a study, and I think we'll hear more about this this afternoon. I'm very excited about hearing that. This is from the really good work that's been done at WETSUS, looking at iron oxide transformations or oxyhydroxide transformations in wastewater being fed into digesters, and vivianites being noted in those systems. So I don't want to say any more about that, because we'll be talking about this later in the afternoon, I'm sure, but it does show that these can form in complex systems. Now, one of the middle authors there, Lordina Eshen, has joined us as one of the ESRs, and I think she'll also be talking this afternoon, working with Antonio and colleagues at AOVARG, helping us with spectroscopy, to look at the optimal transformation of these iron oxides into vivianite. And Lordina's project, again, I don't want to steal her thunder, but basically these are addressing some of the questions that are obvious from the literature. You know, really, what are the constraints on reduction in these complex systems and getting you towards vivianite? How could these be optimized? And you clearly get a range of different minerals forming at the end in these complex systems. So really understanding how they perform in growth trials against reference materials is of interest to us. So that's something Lordina will also be picking up. And I'd just like to, at that point, leave Lordina's name there as an email address. And I know she'd be very interested for collaborators, particularly people that could supply waste iron materials loaded with phosphate for some of her studies. So with that, I'm very happy to stop and pass that back to Sarah.
Thank you very much, John. Very interesting to hear about these microbial aspects, and also a good introduction for the poster session where some of the PTRAP students will present their work, and as well as to the session 3 in the afternoon, where we'll speak more about different strategies for release of phosphorus bound to iron. So I think we have a couple of questions from the audience. So please, Chris.
Yes, from Andrea Hernandez. Can you clarify, please, John, to what extent you're working with pure cultures, or are these kind of mixed cultures in the biofilm? How comparable are your reactors to a sort of real world system?
Yeah, that's a good question. So for our mechanistic studies, we tend to use pure cultures. So well-known organisms like Geobacter and Shewanella that we can manipulate and easily using mutants and study their physiology. But we do try to work with mixed systems, often in microcosms, where we might prime the system with a complex microbial community by adding in donors and iron and looking at their response, and then trying to compare that to what we see in the pure culture model systems. So we do both, depending on the sort of experiments we want to conduct. Are they biofilms or not? That's an interesting question. I mean, certainly in the subsurface systems we work on, they're attached cells most often, but they're not really the thick biofilms that you think of in a classical biofilm system. But clearly in more heavily engineered environments, you can get a thick biofilm that would be similar to a classical sort of multi-micron thick biofilm complex community. And then you've got all sorts of interactions that become important. And I see there's a question about hydrogen evolution, which I guess could be important and would drive the system reducing further if you've got hydrogen production. Some of these organisms might hydrogen cycle as well.
Thank you. Do we have more questions from the audience?
I have a question which is quite general, which is there any potential to simultaneously have a process which from iron phosphate in sewage sludge extracts a magnetite, which is a valuable product, and also releases the phosphorus, which could be recovered for recycling?
Right, so converting the Fe3 substrate with phosphate to magnetite, and then
getting out the iron as a magnetite and the phosphorus out as some available kind of form of orthophosphate or something.
Yeah, I guess those are the sorts of experiments that we really want Lordina to look into to see if that's possible. I'm not aware anyone's been able to do that, but I suppose if you can optimize the system and engineer it, that might be feasible. But I'm not aware of any evidence from the literature or experimentation on that. But it's an interesting question.
But certainly, Chris, I mean, if you can split them, of course, both products are very valuable, so it would help.
Okay, I have another question. You've probably worked out by now that I'm definitely not a chemist. You seem to be indicating that crystallinity of be it iron oxides or iron phosphate, from what I see in the discussion, is an obstacle to plant availability. How come vivianite, which seems to be more crystalline than the iron 3, which is generally amorphous, is more plant available?
Oh, is that aimed at me, Chris, or one of the plant guys? I could take a stab at it if you want, but maybe
any of the panelists are welcome to offer an answer.
Who wants to go first? Yeah, well, look, one of the things I thought was really intriguing, so my thoughts on the system were obviously with some, redox cycling. You'd start off with in the model that's been described, an Fe3 mineral phase with phosphate absorbed strongly, and then if you can reduce that system down, or if you've got a reducing system, where iron's just as an iron oxide without the phosphate, then if you have Fe2 and phosphate together, then you get the formation of vivianite, clearly. And I thought it was very interesting, Antonio's slide, suggesting that when that reoxidizes, you get the slow release of the phosphate, and that presumably makes that more bioavailable for the biomass, for the plant cultures. An obvious question, I suppose, from a microbial perspective is what's the role of microbes in that cycling system? So, these systems are incredibly complex when you start getting other processes running. So if you've got, I guess, for example, denitrification, you might get nitrite production that might help oxidize that system and might help release the phosphate. So, yeah, I don't know if that really addresses your question, Chris, other than to put another layer of complexity that can sit alongside, I think, Antonio's explanation, which was to do with the oxidation of the vivianite and the slow release of the phosphate, which is then taken up by the plant biomass.
Maybe, John, I'll step in here. In our part of PTRAP with the ESR that we have with Rochelle, we are going also testing another avenue, that is using the iron 3 phosphates that are formed in, it could be in wastewater treatment, it could be, iron 3 phosphate that are so-called less available. We will try to identify their fertilizer potential under anaerobic conditions. So in paddy systems, where the iron 3 can be reduced to iron 2 and then releasing phosphor, provided that they're, let's say, readily reducible. So that means no crystal iron 3, but amorphous iron 3 forms. And maybe, if everything goes well, also associated with some organic matter as a local electron source and a shuttle. So that's the idea that we are going to test by testing different iron phosphate iron 3 phosphate fertilizers under anaerobic conditions. And before going to plant test, we will also identify the diffusion profiles of under anaerobic conditions. So under anaerobic soils, add that iron 3 phosphor fertilizer and add an adsorbent for phosphor to map the distribution of phosphor around the granules. So if we have a local hotspot of phosphor, which may serve as a good source of phosphor for a plant growing under anaerobic conditions. So that's one of the avenues. While I'm speaking here, Chris, the previous question before John came in, there was a question about, is it now an advantage or a disadvantage that that the phosphor is poorly soluble? Well, I would say rather disadvantage in general. And I remember there was a very, very nice paper that compared a wide range of recycled phosphor products in their capacity to fertilize. So what they did is they used organic and also organic fertilizers, including char made of sewage sludge. And the paper is from Olivier Duboc from Boku, and who compared the fertilizer potential of all these recycled products in one and the same soils, and found that in fact just a test for the long-term solubility of phosphor from that fertilizer using, say, an infinite bag method, in which you use in fact an adsorbent for phosphate, and you measure on the long term how much phosphor that can be released from that substrate, is a very good predictor for the fertilizer potential. And it's even as good as testing the fertilizer with the soil, just like a soil test for phosphor availability. It's a paper of 2017 for all the people who work with recycled products. I think this is really a very nice illustration that with a good test for solubility, you can predict a fertilizer value with a conclusion that more soluble forms, if the phosphorus is more soluble, it has a higher fertilizer value. So it uses the standard solubility test with alternative ones, and that alternative one, the infinite bag, was the best one in the predictive power. Okay.
I think Olivier Duboc is actually with us. Can he speak, Sarah?
I will just scroll down the very long attendee list.
Yeah, which is not in alphabetical order, which is regrettable, but there's nothing we can do about that.
Okay, yes. Please, Olivier.
Oh, yes, he is there, yeah. And, yeah.
Well, this is his family at the beach is there.
So,
are you there, Olivier?
Yes, I'm here. Can you hear me?
Yes.
Great. That's
Do you want to say a word about your results in your study?
Yes, well, so thank you, Erik, for introducing this study. And actually, that's interesting because right now we are working on an update to this study from 2017. So the basic idea, what we had was to use a sink, so a sort of an infinite sink. So we used ferrihydrite as a test, and so it was a batch extraction of fertilizer, and we let it for several days to several weeks to extract, so that we were sure to get really the maximum out of the phosphorus, the maximum phosphorus out of that those fertilizers. And then after that, we recovered this ferrihydrite, which had absorbed the phosphate. We dissolved it and measured the phosphate, which was adsorbed basically, and that was a very nice indicator, yes, for the phosphorus availability from quite a wide range of potential conventional as well as recycling, especially recycling different types of recycling P fertilizers. So maybe I could, I don't have the name, I should write in the chat the name of the paper, but you can find it under Duboc et al. 2017. So it's in the chat.
Great, thanks very much. I had a specific question about, there are a number of questions about hydrogen, and then we'll come back maybe to some more general things, but some questions about hydrogen as an electron donor. Could you possibly use it to improve reactions in a sewage works? How does it work in your reactors and so on?
Yeah, so I did drop a quick response, a written response, but yeah, I mean, obviously hydrogen's a really good electron donor for these systems, and if you've got that as a potential electron donor, that could help. If you've got excess organic electron donor anyway, I'm not sure it would take you to a different endpoint. I think you'd also need to think quite carefully about the other electron acceptors that could be present there. So, you know, for example, if you were promoting sulfate reduction as well, that would again change the endpoints that you get and take you towards the sulfides. And that might not be what you want, and I think WETSUS have shown that in some of their studies as well. But in principle, it should work as a very good electron donor. You just need to look at the balance with the other reactants in there as well, I think.
Thank you. We're good on time, so I think we can take some general questions for all panelists, if there are some remaining. So maybe all panelists can turn on their videos so that we can see you again. And Chris, I think there were a couple of questions remaining about vivianite.
Yes, there's an overall question that I'm trying to bunch a number of ideas together that vivianite somehow seems to be appearing on the one hand as a kind of new product that people are producing and deliberately changing processes to generate and using as a fertilizer. But on the other hand, I'm also hearing that it's been present anyway, always in digested sewage sludge and so on. So is it really something new and specific? Is it worth trying to modify processes so that we get more vivianite in the sewage biosolids or in the digestate? Or in the end, will it kind of end up all as iron phosphate in the soil and it doesn't really make much difference? So if any speakers have any comments on that.
Let me begin from the wastewater side, so to say, that vivianite will be formed no matter if you want it or not, so that's nothing new with that. What you will hear this afternoon is that it's possible to recover it, to capture it in a fairly pure way and highly concentrated way of vivianite, then so you can separate it from the sludge. And then, of course, what to do with the vivianite after that is if it should be a fertilizer or if it should be reprocessed for further development. That's a different issue. But it's always there. As long as you have iron as a coagulant in the wastewater treatment, you will form some amount of vivianite. Depends on how much iron you dose and some other factors as well.
So is it really worth separating it out in that the sewage biosolids containing iron seem to have a fertilizer value anyway? So is it worth particularly generating vivianite, trying to separate it out if in the end you're going to put it back into soil as a fertilizer?
I would say it depends on the regulations and the quality of the sludge. I mean, not every country is allowing sludge to agriculture, for instance.
I would say from a user point of view, it would be interesting to have a more cleaner vivianite because, as it says, the further processing is also removing various contaminants from the material. And it is for the industry probably easier to work with a concentrated iron phosphate product than with a diluted sludge material, which is, yes, it is containing iron, but to a lesser concentration.
And for that, vivianite is advantageous because it's magnetic, is that correct?
Well, you can separate it, it's paramagnetic, so you can separate it by magnets, yes.
I think one question that was remaining as well from earlier on in this discussion is how vivianite fits into the new fertilizer regulations.
Well, I can maybe answer that myself. Vivianite would be a precipitated phosphate salt and therefore possibly eligible under Strubias, but I would have to look into the detail. I can't remember whether there's an iron limitation in Strubias or not. Do you know that, Bengt?
There is.
There is, okay.
So yep. I think there is a risk that it will not be according to the first round of Strubia.
I think we have a couple of more questions in the chat. Chris, do you want to pick them up or?
One question, is there any full-scale vivianite recovery worldwide? I guess you can answer that, Bengt.
Yeah, I'm taking all the questions for the WETSUS guys later on. So, but there has been one pilot scale plant in Netherlands. So not yet any full scales, but we are keen to go in that direction. So we hopefully can have it within a year or two. We would like to go more on piloting and full scale operations.
Okay, and I would like to come back to the clarification of where vivianite would appear to be a good fertilizer. Is it limited to Mediterranean soils, or is it applicable across Europe?
I think in both, but the major offtake will be in Mediterranean soils. But there is also need in Northwestern Europe for iron.
So there's need for iron also in Northwestern Europe, yes?
Yeah, yeah.
Okay.
But the quantities are less per hectare than in average on the Mediterranean areas.
And I have a second question, which is if you're thinking of applying vivianite, what thinking needs to go into what nitrogen form goes with it? Because we've heard that the, for instance, ammonium can release hydrogen and so facilitate phosphorus uptake. Is that something which is relevant so that in these iron containing phosphorus fertilizer formulations, it might be preferable to have ammonium forms of nitrogen rather than nitrate forms of nitrogen? Is that something which makes sense, or am I going down the wrong track there?
Guy, your microphone is off.
Yes, I'd better say something, hadn't I? I imagine, so vivianite would be more soluble at lower pH, right? So an ammonium source plant root will tend to acidify the rhizosphere, and that should solubilize vivianite. So I can imagine.
That's correct.
I just wanted to comment on this question about management of soluble fertilizer phosphorus sources versus insoluble forms. And generally, for an insoluble or sparingly soluble source, you want finely divided material that's broadcast through the soil, widely distributed, so that there's a large surface area to favor dissolution, versus water-soluble sources where you want to concentrate the form, and then these questions of how you make a nice environment for the roots to access the concentrated form. For triple superphosphate, you can have an extremely concentrated phosphate solution emerging from the fertilizer, a very acidic environment, not hospitable for a root. And somehow match that with these subtle root-induced changes which depend on the nitrogen source. So there's more to it than just ammonium versus nitrate. Sure.
Okay, are there other questions, or panelists wish to make other comments on some of the things we've discussed today? There are questions coming back to the question that iron may be toxic. My understanding was that was only in relatively high concentrations in anaerobic soils. Is that correction? Is that correct?
Yeah, that's correct, Chris.
Okay, are there more questions? We have a couple of minutes left, otherwise I'll wrap up.
What I suggest is we leave the chat open for a quarter of an hour because there are discussions ongoing in the chat and there's no reason to cut them off.
Right. So thank you very much to all our panelists. You can hang on there and participate in the chat for a bit. We have a poster session with 5 of the PTRAP early stage researchers at 1:30. And then at 3 o'clock, we will have the session 3 on strategies for release and recovery of phosphorus bound to iron. So I'm looking forward to seeing you all there. So also please note, as you might already be aware, that there are different links to each one of the sessions.
Yes, so that to register for the next session, it's not the same link that you used this morning.
And I also noted a very good outcome, high interest for this session as well. I noted a maximum of around 230 attendees. So the interest for iron phosphate is really high. So that's very good.
And a compliment to the speaker, most of them are still here.
Thank you.
So people are not just coming and seeing, they're actually staying, it seems, which is good. So thank you very much. As we've indicated, we will make the slides and the recordings of the sessions available afterwards. Just we need the time to check with the speakers, who in some cases may wish to update their slides or change them or whatever. So it'll take a few days and then we'll send you all the links to those. Okay, great, thanks. So time for a break and back at 1:30, and we'll leave the chat open for a few minutes for people who are still exchanging.
Okay, thank
you. Thank you.
And bye.
Thank you, bye.
See you soon.
Bye.